Allô, allô? Très bien. Eh ben, on va commencer. Bon, au terme d'un long processus démocratique, j'ai été élu président de ce comité. Merci beaucoup. Donc, je m'appelle Emmanuel Trella, je suis un local, Sorbonne Université, laboratoire Jacques Williams. Donc, je vais commencer par présenter les membres du jury. Alors, excusez-moi, je vais suivre ma feuille. Donc, c'est ni un ordre alphabétique, ni un ordre d'ailleurs quelconque. Donc, nous avons dans le jury Monsieur Sergio Chibaro, qui est donc à distance, hein, l'un des directeurs de thèse. Monsieur Alessandro Alla, qui vient de Rome, qui est l'un des rapporteurs. Monsieur Iraj Mortazavi, qui est du CNAM. Madame Alena Chilova. Vous êtes d'ici, non, c'est ça ou... INRIA, très bien. Monsieur Sylvain Lamprier, qui est de Nantes, non, Angers. Angers, merci, qui est l'un des rapporteurs. Oui, voilà, je devrais le savoir. Monsieur Onofrio Semeraro, voilà, qui est l'un des directeurs de thèse. Tu es de Paris-Sud, hein, c'est ça. Et monsieur Stéphane Popinet, l'un des co-directeurs de thèse. Voilà. J'ai oublié personne, hein. Non? Si. Oui, toi, tu es invité, mais...
Lionel Matelin,
Comment?
invité. Lionel Matelin.
Voilà, Lionel Matelin, donc invité. Très bien. Et bien donc, monsieur Amine Saibi, on va vous écouter à peu près pendant 45-50 minutes. C'est à vous.
Je vais la faire en anglais, comme ça tout le monde comprendra. So thank you, Mr. Chairman. Thank you, everyone, for being here. I will present to you the work I have done during my PhD thesis, and it's about reinforcement learning and data-driven control of fluid flows. And I will start this presentation with an introduction to set the problem that we are interested in, and then we will move on from there to discuss methods and our contribution on the subject. So in optimal control, we are interested in systems that interact with a certain environment through sensor measurements in order to optimize a certain prescribed objective. So for instance, you can think of autonomous vehicles that have sensors all around, and we have a certain control on the angle of the wheels and the acceleration and so on. And we would want it to act in order to perhaps minimize casualties or material damage and such costs. We can also think of an airplane that would want to maximize its lift or minimize its drag. And another example are wind propellers, on which we have a control on the velocity of the propellers and the inclination with respect to the frontal plane. And we would want to maximize the collected power or the noise trailing behind the propellers and so on. So in all those systems, we have an objective that we want to optimize and a control on the system that acts based on sensor measurements. In our case, we are interested in a particular type of problems that we call spatially evolving equations. And those are systems that depend on space and time. And we start here by presenting an example of such system that we will drag through a big part of the presentation and on which we will illustrate the method that we use. And this example is the complex Ginzburg-Landau equation that is given by this partial differential equation that we subject to a stochastic disturbance. And here, the Ginzburg-Landau serves as a convenient model that features many properties that we find in extended and more complex models. And it is pretty easy to simulate and to do statistics on. And it displays with different sets of parameters, different types of instabilities that we wish to control. Here on the top, we see a contour plot as a function of time and space that shows with a certain set of parameters what we call an absolute instability, which is when a disturbance is growing in a certain region or in space and tends to occupy the whole region. So it's inherently unstable dynamically, linearly. And on the bottom figure, we can see another type of instability, which is a convective instability, where perturbations tend to be dumped in any point of space, but there are just local disturbances that are convected away. And the perturbations here to be sustained have to be subjected to persistent stochastic forcing, where an impulse response will just fade away eventually after being convected in space. So those are two different types of instabilities, and we wish to control them and minimize the overall energy of the system, hopefully. So when we do this, in our experiments, we define a plant for such systems, which are spatial profiles that are coupled with the dynamic of the system. And those spatial profiles consist in an actuator that will be responsible of injecting some quantity into the dynamic here, accompanied with a noise. So the actuations are localized in space. We denote them here by U, localized by a Gaussian-shaped function centered around the point. It goes the same for the disturbance that is also localized in space and is upstream. And we have a sensor that we denote by Y, also localized by those Gaussian-shaped weights, that is responsible of collecting local information about the system. That is then, the purpose of which is to be fed back to the controller that will modify the dynamic in order to achieve a certain optimality with respect to a predefined objective. So the sensor has this shape. It is linear on the state and is localized by those Gaussian-shaped functions. And it goes with same with all those spatial profiles. Okay, so we call this the plant. So then the general problem at hand formally consists in a dynamic that dictates the law of evolution of our system and outputs that are local measurements of the state. And the dynamic is subject to a noisy control. Here, it's a finite dimensional approximation. So after discretization of space with a certain scheme, we are drawn back to a finite dimensional system. And we define a cost associated to any way of controlling this strategy. And the goal is always to find a minimal control for this dynamic. So this is the problem at hand. So now I will go on some classical tools of optimal control to solve such problems and to design optimal controls for the formalism that we presented. And we start by introducing a particular type of subproblems that is very important in control, because often we work within the linear limit for nonlinear dynamics, within a linear limit around a certain equilibrium point, which is for our Ginzburg-Landau the null solution. Then we perturb it. We perturb this equilibrium, and then we wish to either dump the perturbations or stabilize the system to bring it back to equilibrium. So when we linearize around an equilibrium, we get a linear system that has this form. So the data of such a system is defined by matrices A, B, C, and the covariance matrices of the noises involved in the equation. And we call those problems linear quadratic because the dynamic is linear and the costs associated to them are quadratic in state and control. And the goal remains the same. It is to choose a control U that minimizes this cost. And a classic design for such problems, when we know the dynamic of the system, and we know the data A, B, C, and all the matrices involved in the physical model, we can design a feedback controller, U, that feeds back a reconstructed state from observations. So we have observations. We build a reconstruction of the whole state using what we call a Kalman filter. To design the Kalman filter, we need a gain matrix that is denoted here by L, and that is designed by solving Riccati equation. And then this reconstructed state is fed back with a certain gain matrix that is also found by solving a Riccati equation. So those are separated problems and coupled to build and design a controller to stabilize and minimize the energy that we defined. So now this is in the case where we know the physical model. What interests us is to control without model knowledge, only relying on data, only observing the behavior of system with input control and output of sensor measurement on trajectories. So to go one step further, if we suppose we don't know the physical model, there is still a way to estimate the physical model from input-output data. So here we are brought back to a discrete system by a certain marching in time scheme. And then we define a control strategy in the system, we input it, and we collect output data. And from those two time series, we can estimate or identify the underlying system that matches the input-output data. And in particular, in our implementation, we use what we call subspace methods. N4CID and MOESP are examples of such algorithms. And then once we identified the dynamic or the approximated dynamic, we build an LQG controller based on those estimated data. So we estimate A, B, and C, and then we build an LQG on top of it to control the real underlying physical system. So this method uses standard tools in optimal control and has been used even in the fluids community in the last decade. And we want to set it as a benchmark to which we can compare the methods that I will show later. And we see here on the Ginzburg-Landau the performance that we achieve. Here on the left, we can see the energy averaged in time as a function of space, showing that we are able to minimize the energy to some extent. And here is the energy averaged in space as a function of time. So the supercritical case for the Ginzburg-Landau is the dynamics where we have an absolute instability. Okay, so having set the ground with this algorithm, we now switch into tools that are more from reinforcement learning. And in reinforcement learning, well, I don't know if it's clear enough, but yeah. So in reinforcement learning, usually we model the dynamic with a couple of stochastic processes, X and U, that we call Markov decision processes. And essentially, a Markov decision processes relies on two components, what we call a policy that will play a role, the role of the control in this framework. and a transition law that will play the role of the evolution law of the dynamic, which we estimated in the section before using subspace methods. But in here, we wish to bypass for in our work, or in what concerns this, we don't wish to estimate the model's dynamic. We call those model-free methods. So we will focus on those kind of methods, bypassing the system identification procedure to know or to estimate the underlying physical model of the system. So if the system is at a certain time at a state xt, this state will be fed to the policy that then will sample an action that will input into the system. And then with this couple xt and ut, the system will sample the state to which it will transition to. And this is how a Markov decision process models the dynamics that we are interested in. And since we are doing optimal control, we define a cost for this transition, which is a function of the state, the action that is applied to it, and the state it transitioned into. And to every way of controlling this dynamic, we associate a cost. So if we choose a policy and we follow actions that are sampled from this policy, we get a cost, a value function that is associated to it that we call Q pi. And it's the expected cumulated costs during the whole trajectory. So then in this framework, to start going deeper in the mathematical analysis of it, we introduce what we call a Bellman operator associated with a policy, which is in here, an affine function on bounded functions. And it's an affine operator on bounded functions, where here there's the cost that intervenes, the discount factor that appears in the formulation of the value function, and the transition law of the couple xt-ut that acts on bounded functions in this way, integrates them. So this operator allows us to express a very important property on the value functions of policies, which is called the Bellman equation, and expresses the value function associated with a policy as the fixed point of the Bellman operator that is associated with it. Okay, so that's in terms of the language that we use. And then in the scenery of reinforcement learning, we have a class of algorithms that we call actor-critic. And those are implementations where we represent the policy that we call the actor, and the critic that is supposed to be the value function associated with this policy. And we represent them by function approximators. And since we are doing deep reinforcement learning, we represent them with neural networks. Okay? And the iterations of the algorithm go this way. It starts here with a state, yt, or a partial observation of the state, that will be fed to the actor, that will then sample an action that will serve as an input to the environment that is unknown, and it's supposed to be driven by the transition law P. And then the environment outputs an observation of the state it transitioned to, and a cost associated with this transition. And with this, we optimize the critic with some sort of Bellman equation or something that mimics it. And we go to a next iteration of the critic that is a more faithful approximation of the value function of the policy. And now for the critic that we have, we wish to improve the policy to further minimize the value function that we estimated. Okay, so those are what we call actor critic algorithms. Okay, so in this framework, we were interested in describing the dynamic of the errors in fixed point approximations, so in approximations of value functions of the policy that we use, and how it evolves with respect to the policy variations. I think I missed the slide. Yeah. Okay. So from here, this is to set the language of the results that I will present the slide after. So in those algorithms, what we wish to build, I'm sorry for the resolution of the slides. I don't know if it's still readable. But for the algorithms that we are interested in, we are building sequences of actors and critic, pi k, q k. And then to go from such an estimation to the next iteration, what we do is that we improve first the policy with respect to the critic with what we call a policy improvement procedure. So this is lower or equal. Okay, so the next policy that we generate must behave better or have lesser cost than the previous policy with respect to the current approximation of the value function. And then we do a policy evaluation step, and this where lies the choice of our formulation. The policy evaluation step is done with m iteration of the Bellman operator on the actual approximation of the critic. And if m were to be infinite, by the Banach fixed point, it should converge to the value function of the policy that the Bellman operator is associated with. But here we take a certain number of Picard iterates of this Bellman operator on the critic, and then we model the errors in evaluating such operator with a quantity here that doesn't appear well that we call epsilon k. Okay? Those are errors in evaluating the Bellman operator. Since we are using stochastic gradient descent and such, there are always residual errors, and we don't evaluate this quantity exactly. So the critic is not exactly equal to this when it is updated, but up to this error it is. Okay. So in this framework, we wanted to describe the dynamic of the errors in the value function approximation and express it with the policy variations that we can estimate or monitor estimates of practically in numerical examples. So we prove the following identities with the following identity with those notations for the dynamic iteration per iteration of the critic errors that expresses them in some operator convex-like combination between the policy improvement in here that we denote by I and the errors in evaluation of Bellman. Okay, this term is an error related to the initialization and eventually vanishes as k goes to infinity. And we prove an asymptotic error bound also on those errors with means of the sup norm that shows also a kind of convex combination controlled by M between the asymptotic policy improvement and the asymptotic error in Bellman evaluations. And then we fix M, the number of iterations of Bellman operator, which we call the optimistic order. And we do statistics on it to assess how this impacts performance on training in the Ginzburg-Landau equation. So those are statistics for the supercritical case as well. And here we show the average cost during training as a function of the number of episodes. So an episode is a full trajectory of our dynamic. So we see that for larger values of M, we essentially have variations in the policy. So this is an estimation of the variations of the policy on batches. Okay? We see that for larger values of M, the variations in the policy principally occur in the first trajectories that we train on. Whereas for smaller values of M, variations are smaller and tend to trail further away, using more trajectories to reach the performance that we reach for higher values of M. So, okay. Going beyond, I think it misses, yeah. So we can talk about this also. Here we compare reinforcement learning with the reinforcement learning algorithm that I showed. It's an example of a controlled trajectory, comparing the reinforcement learning part with the IDLQG system design that we presented in the second section. We see that the performance between the two algorithms are fairly comparable. So we achieve mostly the same performance. And then we're interested in the impact of the plant limitations on those performances. And here what we wanted to do is do a parametric analysis on the sensor position that would change the structure of the dynamic, which is here xy, that we move along the space axis and train different models to see how IDLQG and reinforcement learning algorithm presented compare in terms of the performance that is achieved. So for the supercritical case, we see that also they're fairly comparable in performance. But then IDLQG, more often than the reinforcement learning, tends to inject energy for sensor positions that are more extreme, but it's not striking in here. Second thing that we can see is that we have a certain region where we have more performance than the not controlling, which is roughly between -5 and 20. And this is related to the spatial support of the only unstable mode of the complex Ginzburg-Landau equation in supercritical regime. So it's a dynamic that is driven essentially by one unstable mode. And as soon as the sensor is positioned here between -5 and 20 roughly, we are in an observable or detectable setting, and we can achieve some performance. So this we were interested because sometimes in the reinforcement learning community we didn't find assessments of such impact of observability deterioration and its its consequences on performance. And it goes the same for the controller, since observability and controllability are dual problems. The control has to be positioned in the spatial support of this adjoint unstable eigenvector. So now, turning into the subcritical case. So a subcritical case is linearly stable. And the disturbance of such system is dumped after a certain time, convected away but dumped, as we can see here in the impulse response of the system. So we just do an impulse at position x equal minus 14 in here, and then the perturbation eventually is dumped. So we keep it persistent with a continual stochastic forcing. And what we see in the impulse response, that there is in the spatial temporal plot a certain inclination of the solution, which shows that between 2 points of space there is a delay for the information to go through one point to another. So there is a delay in propagation of information due to the convective nature of the system. And when we do statistics on the system, which we see even more striking deterioration in the IDL-QG case, where it pumps more energy, even more energy, than in the supercritical case for sensor positions that are deteriorating drastically observability. And the region of effect here also, a second point, is narrower. We have roughly between -5 and 10, where we achieve a certain performance that is better than not controlling. And what we see also is that in reinforcement learning, we tend to settle on the null control in case the sensor doesn't have any meaningful information about the state, where observability is drastically deteriorated. So yeah, the region where we have an effect is narrower than the region of space where we have a concentration of the least stable eigenmodes of the system. So this brings us to the next section, where we wanted to study more spatio-temporal limitations of the plant. So for this, we introduce another dynamic, which is the modified Kuramoto-Sivashinsky equation, which displays a more pronounced convective instability, where we can, with stronger delays between the spatial components, we can assess what are the determining factors in building or designing a performing controller. So we see here a spatio-temporal plot of the solution, where we see that the inclination is more pronounced than in the subcritical Ginzburg-Landau equation. Okay, so the plant in our case is sketched in here. So we still have upstream a disturbance input, and then it is source of a persistent disturbance, stochastic forcing. And then further downstream, we have an observation sensor Y, as in the previous case. And then we have an actuator U that will input controls to change the structure of the flow. And then here we add also further downstream cost sensor Z that will assess how the actuator is taming the perturbation that goes through it. So in here we have a lag between, or a delay in the propagation of information from the disturbance to the sensor, and then by the time it reaches the actuator and the cost sensor. So what we want to do is to not identify the underlying physical system, but just get information on the delay between the observation sensor and the actuator, so to calibrate it and so that it can act on the right observations. So to do so, we have some sort of pre-training procedure, so that constrains the two first trajectories that we generate during training. The first trajectory is a free trajectory where we don't control, and the signals from the sensors Y and Z are shown in here for such a trajectory, where we see a certain shift between those two signals. And a second trajectory, which is acting upon sensing. So as we suppose the dynamic is Markovian, and then as soon as we observe certain information that arrives to the observation sensor, we act upon it. And we still even see a smaller lag here in the sensor signal, the observation one and the cost one. And the first, the top figure and the shift that appears in it corresponds to the delay or the lag between the sensor Y and the sensor Z. And the shift that appears here is the delay between the actuator U and the cost sensor Z. Okay, so the difference of the two. So those delays we estimate with a cross correlation function that represents the integral overlap between the two signals, and then the shift that maximizes this quantity corresponds to the time delay between the two signals. So we retrieve two delays from this trajectory, the one corresponding to the distance between the sensor and the sensors, and the one corresponding to the distance between the actuator and the cost sensor. And the difference of the two correspond to the distance between the observation and the action. And we do statistics on sensor observation to see if this procedure can assess the real delay that we can retrieve from the supposedly unknown dynamic, which is in here. And we see a pretty good match between the estimated delay and the real delay of the underlying dynamic. So this is done to validate our estimation procedure. So why do we do this? Because if we run the reinforcement learning algorithm that I showed without taking care of the delays, or without instructing the different components of the algorithm with the right delays, we don't have any performance achieved. We don't have any training that is possible. And then when we change the policy and the critic to rely on lagged observations, we start to get some performance observed. So this shows examples of those performances on the modified Kuramoto-Sifashinsky equation. Here is the energy averaged in time as a function of space. The actuator is at position 400, so we see that the perturbation starts to be dumped at this point. This is the energy in time averaged in space. And this is a counterplot of the solution showing how the persistent disturbance is dumped or tamed starting position 400 where the actuator is located. And this is the prescribed running cost signal that we supervised with the training, which is the square of the cost signal that we get from the cost sensor. Okay, so having done this, we wanted to exploit further the estimated delays that we had with this procedure, and we were interested in the credit assignment problem and how it is expressed in this setting. And so the credit assignment problem is, how do you associate variations in the costs to the actions that are responsible for them? So in this setting, since we have a physical model, we can express it quite nicely with the delay that there is between the action and the cost sensing. So an action will have consequences that correspond in the future to the cost that we observe at the delay time that we estimated between the actuator and the cost sensor. So what we did in the algorithm is that we did statistics on M for two different cost sensor positions by supervising the critic with rewards that are going from the instantaneous reward and collecting all the rewards up to a certain look-ahead time, that is here M, and then bootstrapping with the approximation of the critic from there. And we see that for those two sensor positions, so the actuator is at position 400. This is a position that is further away from the actuator, and this one is pretty much closer. And we see that the behaviors when we vary the look-ahead parameter M is changing. When the cost sensor is further away from the actuator, we observe that we have noticeably better performance for far larger values of M. We need to collect far more costs in terms of time steps that we look ahead into and that we sample from the trajectory. Whereas we need a bit less when it comes to sensor positions that are closer to the actuator. So then we fix this look-ahead parameter as the delay that we estimate to be the corresponding to the distance between the actuator and the cost sensor. And here in red, it shows that we essentially get the same performance that we get in the best cases where we were varying M unguidedly. And then we compared this also to another mode of supervision where we didn't bootstrap with the Q function. We just supervised by the lagged costs corresponding to the delays between the actuator and the cost sensor. And we observe how they compare in this figure. So it always acts on delayed observations and on lagged costs. So the modified Kuramoto-Sierczynski was introduced as a model to mimic what is happening in the Blasius boundary layer. And it shares the same, at least, delay features as this one. So we apply the methods and the algorithm that we developed here into this particular case. So we interface our reinforcement learning algorithm with a finite element solver, which is Dolphin X. And then we run training on those trajectories to control the perturbations that are persistent in the domain. And we keep essentially the same plant than in the Kuramoto-Sifashinsky equation, generalized to a 2D model. So the Gaussian-shaped functions are in XY space and have local effect. And here in the space domain, we see how the perturbation evolves. So on the top one, we have the uncontrolled dynamic. And in below, we have at space position 400, we have an actuator. And we see the comparison between the evolution of the perturbation when we are controlling and when we are not. And this is the energy in time for this system. And this is the cost signal that we wanted to minimize. So to summarize, in what we did, we were interested in assessing the impact of plant limitation in different regimes and for different systems that show a variety of spatial and temporal features. We did an error analysis of a certain formulation is embedded into the approximate modified policy iteration framework that is based on the policy variations. We proposed the method to handle the loss of non-Markovianity in dynamics that exhibit time delays. And we do this solely relying on data. And what we wish to do in introducing those delays and so on is not to increase the dimensionality of the represented components of the algorithm. And then there's the implementation and the code that will be open sourced, which principally we used PyTorch interfaced with some numerical scheme that we tailored to the dynamics that we presented. And for the 2D case, we interfaced with a Dolphin X solver. And then as a matter of perspectives, there is a remaining work that is ongoing that aims to generalize the approaches that we propose to multiple delays and eventually varying in time or delays that are functions of space. And there is also an analysis of, as I said, the diversity of implementations and the different ways to realize those actor-critic algorithms. And this goes by also structuring the errors that appear and qualifying them as coming from either the expressivity of the functional approximations that we use. There is also the optimization loops that are involved. And structuring those will allow us to go further into the analysis of the errors and how they propagate. On this, I thank you for your attention.
Okay, thank you very much, Amine. We are now going to questions, and we will start with referees. So I will pass the